Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin our 59th CoCoRaHS Weather Talk webinar. Thanks for joining us today. I'm Noah Newman, filling in for our regular host, Henry Regis, who is unable to be with us today. We are coming to you live from the Colorado Climate Center at Colorado State University in Fort Collins, Colorado on this warm midsummer morning. We'll be recording today's broadcast for future viewing. In fact, all of our past webinars are viewable via the CoCoRaHS website or our YouTube channel. Finally, all of our Weather Talk webinars are sponsored by the generous donations of listeners like you. Today, we will be exploring Mesoscale Convective Systems, or MCSs. These are large lines or clusters of storms that regularly move across the country and account for a major portion of the summertime rainfall in the central United States. With us today is CSU's very own Russ Schumacher. Russ is a longtime friend of CoCoRaHS. He is an associate professor in the Department of Atmospheric Science here at Colorado State University, where he conducts research and teaches courses on the topics of mesoscale meteorology, weather systems, convective storms, and weather prediction. Russ joined the CSU faculty in August 2011. He received the Career Award from the National Science Foundation in 2010 and was selected as an Outstanding Professor of the Year by the students in this department in 2012. He also currently serves as the editor of the AMS Journal Monthly Weather Review. More famously, in fact, Russ is known for a successful run on the quiz show Jeopardy! Winning in 2004 at the Tournament of Champions, and then he was actually invited back for the Battle of the Decades, where he made it all the way to the semifinals. So thank you, Russ, for joining us. Maybe we should start out today with a Jeopardy! Question. Maybe, how about heavy rain for 100?
Sounds good, Noah. Thanks. Yeah, thanks everybody for being here. I'll come back to that topic a little bit later on. But yeah, I appreciate all of you calling in here to hopefully have a nice discussion about a topic that I study in a lot of my work, and that probably a lot of you are familiar with in experiencing them, even if you didn't know sort of our technical name for it. And I also just want to thank all of you for your contributions to CoCoRaHS, because the kind of data that you all provide is a big help when we're studying these, especially looking for heavy precipitation, which is kind of the main topic of my study. So I'll fire up my slides here. Hopefully that'll show up nicely. I also just want to acknowledge a bunch of people who are listed here, mainly my former and current graduate students here at CSU. So I'm going to start off by just showing you hopefully a bit what these things look like, what these mesoscale convective systems look like, and then we'll talk more about the definitions and some of the details in a bit. But I'm going to start with an animation, and I apologize, those of you on slower internet connections, this may not come through the greatest, but if the animation doesn't look great, I'm going to step through sort of some key time periods in it here in a second. And so what I'm going to show you, it hasn't started running yet, but what I'm going to show you is some data from our amazing new GOES-16 satellite. So this is the new satellite that NOAA and NASA launched back in last fall, and is not operational yet, but is getting close to that stage where they're testing out the data, and just the stuff that we're seeing is incredible, and probably maybe you've seen some of these images online or whatever. But what I'm going to show you here is basically an animation of a 3-day period a couple of weeks ago, so from the 27th through the 30th of June. The images are going to show what we call infrared imagery. So it's basically the satellite looking down and measuring the temperature that's being radiated up to space. And so where you see colors on here, like the blues and greens and yellows and oranges, is where the tops of the clouds are really, really cold, which means that the storms are really, really deep, extending up far up into the atmosphere. And so what I'll do is I'll just get this loop started, and we'll go through it a couple times, and then I'll point out some of the key features. So what we see here, so this is what the storms look like on the satellite imagery, and this is one MCS here on the 28th of June, or kind of the 27th into the 28th. Another one here, and then we'll see that one dissipate overnight, and then a third one will pop up here very dramatically over Kansas and Oklahoma right in here towards the end of the loop. So I'll run through this one more time. So there's just, I mean, we could probably spend the whole hour just kind of picking apart all the stuff that's going on in this animation. It's just all sorts of interesting details going on in the storm. So here's that second MCS over Iowa and Missouri, and then we'll see that one weaken, and then things are kind of moving to the south, and we'll see this third one erupt here over Kansas and Oklahoma there, and then moving off to the south. And so, you know, you may have picked out all sorts of interesting features in this, and I'll show it one more time after I step through some of the things that I pick out here, and kind of just give you a sense for what these systems are, how they develop, where they tend to form, the times of day when they tend to be active, and so forth. And so I'll just step through a few of the times here that we looked at, just to give you a sense of this. So this is from the afternoon or early evening of the 27th of June. And what we see are storms developing here in eastern Colorado, western Nebraska, eastern Wyoming. And this is a pretty typical place for storms to develop in the late afternoon. There's upslope flow of moist air towards the Rocky Mountains, and that often gets storms going in the afternoon and early evening. And you know, they will intensify, and then they'll move east through the evening and into the night. And so this is at about 5 p.m. Central Time. If we go forward now, about 6 hours later, and now we look at those same storms that were just getting started over Colorado and Nebraska have now grown into these large mesoscale convective systems. And, you know, it kind of depends how you define it. There's certainly one big one here. We might even call this a separate one down here, and another one up over North Dakota. But in any case, what you see is those initial storms have grown into these large systems over the central U.S. In this particular case, this system across Nebraska was moving across and producing very, very intense winds, with reports up to 100 miles an hour in some areas in central Nebraska. And so, if any of you on the line are from that area, you might have experienced that back on the night of the 27th into the 28th. And so this is at 11 p.m. And now if we step forward into the morning, so this is 12 hours later, what we see now is that system has moved over to Iowa and Minnesota and Wisconsin, but it's really dissipated. And this is a pretty typical evolution where these systems are strongest in the nighttime and then weaken in the morning. And probably a lot of you have just experienced this, depending on where you live along this track, that this is a pretty typical pathway, and I'll try to explain why in a little bit. Okay, so this is the morning. Now we go to the next afternoon. This is 5 p.m. Central again. The storms are starting to develop over Iowa, mainly over Iowa, some in Minnesota and Wisconsin. So this is the late afternoon. We go to the evening here. You also see in the afternoon, again, storms forming east of the Rockies there. So we go to the nighttime. This is 10 p.m. Central. We've now got this big MCS across the Midwest with this part over southern Iowa and northern Missouri producing some very heavy rain because it's not moving very much during this time period. So this is sort of the heaviest rain going on in this area. And then we go to the next morning. So this is noon the next day, and the system is still going a little bit, but it's certainly much weaker than it was the previous night. And now we step ahead to the next night. So this is at, now 1 in the morning a day later. And you see those storms have blown up again over Kansas and into Oklahoma. And so we see on these 3 nights, 3 sets of MCSs, and this is a very I mean, these are maybe particularly strong ones, but this kind of progression is very, very common in the central U.S., and we'll try to get into some of the reasons why this happens. So I'm just going to play this satellite loop one more time so you can take a look at it again and look for some of those features we were looking at. So there's the one over Nebraska and Iowa, dissipates into the morning, new storms in the afternoon and evening, the heavy rain with the slow-moving system over northern Missouri, weakens into the morning and early afternoon, and then late afternoon, evening, storms erupt again over the plains and so on, and then into the following morning, things start to weaken again. Now, I showed you this satellite imagery, and you might be used to looking at infrared satellite imagery like this. It's, you can find it on the web, or often they'll show this on TV. But it's maybe not the product that you're most used to looking at. But the reason for showing it partly is we have this nice new satellite that I wanted to show off some data from, but also when people first started studying mesoscale convective systems, this was the type of imagery they were looking at. It wasn't nearly the level of detail or the time resolution that we have now, but we were looking at it from space from this sort of picture. What you might be more accustomed to looking at is what these look like on radar. And so I'll show you that too for this exact same time period, just to give you a sense of the similarities and differences of what these things look like when you look at them with the ground-based radar, as opposed to looking down on them on the top from space. And so I'll loop through this here. So there's that line that went across Nebraska with the 100-mile-an-hour winds. The storms weaken. Here's the new ones over Iowa, the heavy rain over Missouri. Again, that system weakens into the morning, and then here's those storms erupting over Kansas and Oklahoma there and moving off to the southeast and weakening again. So some of the things look similar. We can get the similar progression, but there's also some different details that we can see. We can kind of see maybe the finer scale structure of where the strongest storms are. That's harder to see from the satellite perspective, but we can see that in the radar. You can also kind of see some more of the details of how the storms are moving and interacting with each other. So I'll show bits of both types of imagery as we go through the talk here. And so why do we care about these? Well, as you could probably guess, they're producing severe weather, as we talked about, but they're also really important for the rainfall characteristics in the central United States. So here's just one way of looking at that, which comes from your observations, the CoCoRaHS network across the country. And so I'll just step through those 3 days we were looking at. The light blues here that you see are sort of the, small to maybe modest rain amounts, which these mesoscale convective systems are really important for producing for the agricultural regions of the central United States. But what we also start to see are some of these really big values, the dark blues and into the yellows, and we'll see some oranges and reds where it's maybe not the rainfall amounts that you're hoping for, but instead the ones that start to produce issues with flooding and so forth. So here's that first day. You can see that one was moving pretty fast, and so we don't see a lot. We see sort of a broad swath, lots of these, light blues and purples, that's the kind of rainfall that you want. You need that rainfall for your, for your cornfield or for your lawn or whatever in the summertime. So that's the nice kind of MCS that we see, although maybe not the 100-mile-an-hour winds is not what we're looking for. But we go to that second day, and now we see, say, that little spot over northern Missouri where the storms had stalled out. That's where we're getting up to 10 to 12 inches in a day, which is not the sort of rainfall amounts that are necessarily helpful, but instead lead to flooding issues. And then here's the third day. We have, again, sort of some broad swaths of those lighter amounts, but with the really heavy amounts embedded in some areas as well. And so this is, this kind of data that you all collect through CoCoRaHS is really key, along with the radars and other networks to study the rainfall characteristics of these systems. Okay, so what have we seen from these loops? We see that these large lines and clusters of storms often develop over the central and eastern United States. From the loops that we showed here, and as I'll show from just long records of data, We know that they're typically the biggest and strongest from the evening to the overnight hours, and then they often dissipate in the morning or the early afternoon. They produce these beneficial rains over a large swath of the country, but they can also produce hazardous weather like severe winds, hail, and extreme rainfall and flash flooding. And so all of these big clusters and lines that we've been looking at, we kind of lump into this catch-all name of mesoscale convective systems, or MCSs, and we'll now kind of get into what the details of some of those. So first, let's try and just describe what each of those names, those words are in that name. What do we call the mesoscale? Well, meso, you might know, the root of that just means middle, and so it's this middle scale in the atmosphere. In between the microscale, which is real small scale stuff like you know, individual clouds, say, or things like that, and the large scale, which would be big, you know, winter storms, or, you know, extratropical cyclones and things like that. And so the mesoscale is in the middle, and I think it's still a good way to describe it is where one of the places it originally came from was for things that are too big to see on a single radar, but too small to show up on a, you know, a weather map of the United States. Now, of course, we have better data, and so we can show some of this stuff on a big map of the United States, but that's kind of how people were thinking about it. So it's this middle scale, and we'll get more into that as we go along here. Well, so it's mesoscale convective systems. What do we mean by convective? Really, it's just, you know, you can think about it as thunderstorms being the main mode of convection that we see in the atmosphere. Convection, sort of generally in physics, is just energy flowing in a fluid from warm to cold. So it's one of the three methods of heat transfer, right? Radiation, convection, and convection being one of those methods. And so in the atmosphere, this is usually moving of warm, moist air that's less dense upward. So it's transporting heat from near the surface upward. And usually we think of this in deep, moist convection, so these deep cumulonimbus clouds. Or thunderstorms. This is just a picture that I took a few years ago where you can really see, you know, you can see that bubbling, and that bubbling up at the top of the clouds. That's the convection. The warm, moist air rising, the water vapor condensing into liquid water, making clouds and rain. And so that's the convective process there. And then system, just, I think, you know, we use that because these clusters and lines are more than just the individual thunderstorm cloud. You can see that all of this is interacting with each other, and so it really is kind of a system rather than just a collection of individual clouds. And so the kind of formal definition that we use for an MCS that comes from the American Meteorological Society glossary is a cloud system that occurs in connection with an ensemble of thunderstorms. You know, you can think of that as like a group of thunderstorms, and then produces a contiguous precipitation area of 100 kilometers or more in at least one direction. So it's the sort of things we were looking at in those satellite and radar images earlier on. Now, where this gets a little bit confusing is that, so the MCS is sort of a catch-all term for anything that's these organized systems of thunderstorms. But then, you know, in our research areas, we like to make up lots of additional terms to describe certain specific types of these. And so there's probably 15 different types of MCSs that you might hear about, and I'll show what examples of some of these later on. But there's the mesoscale convective complex, which I'll describe. These are big circular systems as viewed by satellite. Squall lines fall into this category, bow echoes, and various other types. And so this is just one way to kind of try and graphically depict that. So the purple circle here is MCSs, which encompasses all of these other different types like squall lines, bow echoes, mesoscale convective complexes, and we could throw some other names in there too if we wanted to. So MCS is this general term, and then there are some specific subtypes that I'll talk about here as we go forward. Okay, so why do we care about these? Really, across a bunch of different regions in the world, MCSs are a huge producer of the rainfall in the summertime. And so they really drive where agriculture is favored in different parts of the world. In the central U.S., this fraction can fall somewhere in the 30 to 70% range of the warm season rainfall in the Midwest U.S., and there's some parts of the world where that number is even higher. There's lots of hazards, which can include, like I said, damaging hail, winds, lightning, of course, flash flooding, and so they contribute a lot to the water cycle and just to the general circulation of the atmosphere. And so one way to look at this from another satellite picture is to look globally at how important these are. And so really I just want you to point to these two that are in the red boxes here. So this is sort of the general MCS category in the upper right, and then the biggest and strongest MCSs are shown down here in the bottom right. And what the colors are here is the fraction of rainfall, total rainfall in the year that comes from MCSs, either generally or from these large ones. And you see certain regions of the globe where these, you see these red colors where this is up over, 60, 70% of the total annual rainfall comes from these MCSs. So I guess maybe we'll just focus on these large MCSs down here on the bottom. Places you might notice, this particular map, this satellite that we're using here only covers about the southern, quarter of the United States, but you can see the values get big there. Again, maybe 50+% in the southern and central U.S. of the rainfall. If you look in Central Africa here, most of the rainfall comes from MCSs there. And then in South America, Argentina in particular has a huge fraction of its annual rainfall that comes from these mesoscale convective systems. And so now I'll kind of try to explain some of these subtypes that we look at, what they look like on radar and satellite. One of these types is what is referred to as a mesoscale convective complex, or MCC. So these are really among the biggest MCSs. They look circular when you look at them in satellite. There's sort of some specific definitions here, but they're a bit arbitrary, and the details are not that important. But when you look at them on, say, infrared satellite imagery, they look like this. They're almost circular. I mean, they're never going to be a perfect circle, but they're roughly circular in shape with some very, very cold cloud tops. That's what the reds and yellows are here. So as the satellite is looking down and measuring the temperature, it's very cold there, which means that it's seeing the top of a cloud that's very, very high. 50 or 60,000 feet potentially at the tops of those thunderstorms. So this is just one example from back in 2014 of what this looks like on the satellite imagery, and here's what that same system looks like in radar imagery. So you can see that the perspectives give you a bit of a different view. Here in the satellite image, you're seeing just sort of this big circular region, and there's some stronger storms in here, but you don't really know quite what they look like. The radar maybe doesn't measure the whole swath of the system because it's only looking at where rain is falling, really, as opposed to where the clouds are. But you can see there's like this strong line here in southeast Kansas, northern Oklahoma, and then a broad region of lighter rain off to the north behind it. And so this is kind of a typical comparison of one of these MCCs in the central U.S. in the satellite and the radar perspective. And as we looked at that image earlier of the fraction of rainfall, this is just another way of looking at where these occur. You can see the places where they tend to be favored, in particular, the central plains of the United States and the Midwest, South America, and particularly Argentina, Central Africa, and then also parts of Asia, like in China, and some in Northern Australia as well. So mostly these big MCCs occur over land. They tend to occur downstream or in the lee of some elevated terrain. So in the case of the U.S., to the east of the Rockies, with the large-scale flow going from west to east, and these form then east of the Rockies. The same is true east of the Andes in South America. And worldwide, they mostly occur at night. And if we just compare this map of sort of, counting them up to this map on the bottom where it's fraction of rainfall, you see they line up pretty closely there. Okay, and so I mentioned they tend to occur at night, and this is a slightly older graph, but you can kind of get the picture of what's going on here. What this shows along the x-axis here is the local time, so going from 5 in the morning to 5 in the morning the next day, and then 5 p.m. the next day. And then this is just kind of the number of MCCs that they showed, and there's 4 different kind of graphs here. The first one here is when the first thunderstorms form, and sort of the peak here is at about 1 p.m. So early afternoon, kind of into the late afternoon and evening is when the first storms tend to form. And then initialization here is when it first reaches that big circular criteria. So this is when it becomes a big system, and that peaks at about 9 p.m. local time. And then this darker gray one is when it reaches its largest size, which tends to be about 1 in the morning. And then when it dissipates is over here in the back, and that is at about 7 in the morning on average, or sometime in the morning to early afternoon. And so this is really, it's a very distinct diurnal cycle, or kind of evolution, where it's early afternoon the storms form. Shortly after dark is when the system grows to this larger scale, to the mesoscale, gets its biggest at 1 to maybe 4 in the morning, and then dissipates in the morning to early afternoon. So this is really sort of a curious pattern that we see here. It maybe doesn't make a whole lot of sense when you first think about it, because usually when we think about thunderstorms, the sort of fuel for the thunderstorms is the heating from the sun of the ground, heating up the ground. That's where that moisture, that warm air that's less dense, and you have moisture in the air, that's when the thunderstorms tend to get going. But what we actually see is this overnight maximum that's very prominent, at least here in the central U.S. And so there's got to be some explanation for this other than just the energy, heating up the ground of the sun, because these storms are actually becoming their strongest well after the sun has gone down overnight. And so we'll kind of explain a couple of the processes that lead to this. And here's just another way of looking at that same cycle. I love these animations. What it is, it's basically the average over 10 years or 11 years of data in the summer from radars, and what it shows is sort of where you get to these yellow and red colors is the rainfall amount in that area, and then it's cycling through up here on the top. If you look, it's cycling through the day, and this is in Zulu time, so if you subtract 5, then you get central time. But in any case, what you see is this very distinct cycle of storms here forming over the Rockies and then moving out into the plains in the Midwest. And this is the signal of those MCSs initiating, like we saw in that first satellite image, over the mountains, and then moving out overnight into the plains, and then dissipating the next morning somewhere over the Midwest. So it's a very repeatable type pattern in that area that you can see even when you average data together from 10 years. Okay, so why is there this nocturnal maximum? Why are the storms strong at night as opposed to in the afternoon? The biggest explanation for this is what we refer to as the Great Plains low-level jet. It's the increase of winds just above the surface at night that is really maximized. This is from one of the first studies looking at this. Really maximizes over the Great Plains of the United States. So this is basically just how many times one of these low-level jets happened in a couple of years. In these different areas, and you really see this maximum over Oklahoma, Kansas, Nebraska. And so what happens is at night, the winds, again, just above the surface, really rev up over this area almost every night that this happens. And so there's two kind of different sets of processes that can lead to this. One is just if you have a strong pressure gradient, right? This is why winds are stronger or weaker in general. you know, if you have a weather system moving through with a low pressure, that tends to increase the pressure gradient, which then increases the wind. So we have that process, but that isn't necessarily distinct to night or day. So we have that process, and then we have another process that is really most important at night. And we could spend a bunch of time kind of going into the details of this, but basically what happens is in the daytime, because the sun is heating up the ground, there's just lots of mixing of the air. The sun's heating up the ground, which then makes it less dense, that air less dense, so it rises and it mixes everything up, which tends to make the winds sort of constant with height, at least in this lower layer, or not varying all that much. But after dark, that heating shuts off, which shuts off the mixing, and so now right near the surface, the winds tend to get fairly weak overnight, right near the ground, but just above the ground, then the winds really start screaming. And so this is what that nocturnal enhancement is. And over the central U.S., a lot of times you add these two things together. You have this sort of general weather pattern in that area, plus this nocturnal enhancement to really increase these winds in the central U.S. And this is just an example of what this looks like in some data, really high-resolution data that was taken in a field project that I'll come back to later a couple of years ago. This is just an example from Kansas. It's the wind speed where the blues here are, so like this blue here is 22 Z, which is 5 p.m. local time. So you can basically see, I mean, right near the surface, the winds are a little weak, but otherwise above that, it's about constant, 10 meters per second or about 20 miles per hour. But then as we go into the night, so this next one is a couple hours later and a couple hours later, and then we get into the night, we see the winds near the surface are even weaker, almost down to zero. But up at about 500 meters or so, or 1,500, 2,000 feet, the winds are really, really strong now, up to like 50, 40, 50 miles an hour in that region. And this is really repeatable. And so this is that low-level jet. This is what it looks like, is the winds weakening near the surface, but really strong up above. And so what that low-level jet does is it brings warm, moist air, generally from our moisture source, which is the Gulf of Mexico. So you have this warm, moist air in the Gulf of Mexico. This low-level jet starts bringing it northward, and everything kind of comes together where at the so-called nose of that low-level jet, or where it ends. And so where that low-level jet ends is where there's lots of these MCSs and lots of precipitation. And so this figure is a little blurry, but hopefully it kind of gets that picture. So what we see here, I'll mostly point you at this panel, where the solid lines here are the low-level jet speed, the winds at 900 millibars, which is kind of roughly where that wind peaks, maybe a few thousand feet off the ground. And so you can see it's maximized in that region, Kansas, Oklahoma. The low-level jet is really strong, bringing the warm, moist air northward up into the plains. And then the shaded field here is the rainfall over this period. And so what you see is where that low-level jet, sort of at the nose or the end of that low-level jet, is where now you're sort of converging all of the air into that region. It's warm, moist air, so it tends to be conducive to producing storms and rainfall in these MCSs. And so you get these corridors of lots of rain for many days in that region. And so what's kind of interesting about this comparison that was done in this study is it compares these days over here on the right, which was days that had a low-level jet, and you can see all that rain, with days over here on the left that had no low-level jet in those same years. And so what you can see is when there's no low-level jet, there's very little rain over the central U.S. And so when that low-level jet is not active, it tends to be very dry. But when the low-level jet is active, it's very wet, and it's when these MCSs are really frequent. And so this low-level jet really is kind of the fuel in a lot of ways for these nighttime convective systems to develop and produce so much rain over the central U.S. and that it's at night. I'm just going to skip over this one for now. But this is just another way of looking at that same thing. This is like how many of these MCSs do you get per week in the summertime? And in that region where the low-level jet tends to be just north of where it's strongest, you might see 3 to 4 of these per week on average. Some weeks it would be even more than that. In this region of Nebraska, Iowa, northern Kansas, off into Illinois and Indiana, and it's no surprise or no coincidence that this is the region where a lot of our agriculture is developed in the United States, because these MCSs are so repeatable and producing so much of the rain there. Okay, so I'm going to move on now just for a little bit and kind of explain some of the ins and outs of these, or give you a sense of how we understand them scientifically, and a little bit about forecasting. And we've alluded to all of these factors already in this presentation, but if we boil down thunderstorms or deep moist convection to their most basic ingredients, there are 3 that you need. You need moisture, right? If you're going to get clouds and rain, you need moisture. You need instability, so this is basically, you need the air near the surface to be less dense than the air aloft, so that you can get these really strong rising motions. And then you need lift. You need some initial lifting mechanism to kick that whole process off and get the storms going. So those 3 ingredients are just crucial. You won't get thunderstorms if you don't have all 3 of these. And then there's a 4th ingredient. If we want severe convection or organized storms, there's one 4th ingredient, which is what we call vertical wind shear, or the wind changing in speed or direction as you go up with height. We looked at that figure showing the low-level jet. That's a great example of vertical wind shear. You have very strong winds at one layer and then very weak winds at another layer. And so this process acts in a lot of ways to help to organize the storms and make them stronger. And I'll kind of describe why vertical wind shear is so important. And so this top panel here is just kind of a very, very simple depiction of a thunderstorm in an environment with no vertical wind shear. So this is just, you just have sort of weak constant winds at all levels. And so what happens is the clouds start to go up, you form rain, and the clouds and the rain starts to fall. As that rain falls, some of the raindrops evaporate, which leads to cooling. And so that cold air is more dense, so it sinks and comes down to the ground and spreads out. But if you have no vertical wind shear, basically that air just comes down, it sinks, it spreads out, and then that's the end of it. That storm will dissipate very quickly, within 15 or 30 minutes after this time. Okay, so this is what happens when you have no vertical wind shear. If you add in this change in the wind profile with height, so here is an example where, say you have a wind profile that looks like this, with sort of weaker winds at the ground and going to very strong winds aloft. This would be what we call westerly shear, so the westerlies are increasing with height. Now you get that same initial thunderstorm, the cloud goes up, you start to produce rain, the rain sinks, the rain falls, the cold air, the air evaporates and produces this cold air. Now what happens at the edge of that cold air, so this blue here is the edge of that cold air, the outflow going out from the storms. You've probably felt that before when the storms are just about to arrive and you feel that rush of cold air and the wind shifts. So that spreads out. But when you have wind shear, what happens is you actually create more lift at this leading edge. So the way we often think about this, right, so you have this wind shear, and if you put a pinwheel in that, right, like some giant pinwheel, it would start to spin like this, and that's what this little purple arrow is here. Within this cold air, you have a pinwheel going in the other direction, and those two basically interact to lift the air at the leading edge and form new storms. And this is how one of these mesoscale convective systems gets going, is you lift air at the outflow, which forms new storm cells, and this can go on and on and on for hours in this environment. Whereas if you had no vertical wind shear, you only have one of those pinwheels, not the other one, so you're lifting air just a tiny bit there, and it's not developing into new storms. So that's sort of it's this key factor that that really helps to make these things grow and become these large systems. And so how do they tend to become organized? The most common way that this happens is so that what was done in this study was actually just looking at lots and lots of radar images over lots of these MCSs and looking at how the shape of them basically as they appear on radar imagery. And the most common way that this happens is you have some storms, individual storms that form into a line, and then behind that line is this region of lighter rain, which we call the stratiform rain. So there's convective rain, which is very heavy, and then stratiform, which is lighter. And most commonly, they go in this way, where the stratiform rain is behind this line of convection. But it can also happen where you get the stratiform rain out ahead of it. This is like 19% of the cases, or where it's parallel, and that's another 19% of the cases. So, but still, the most common one is this one up here, where it's behind. And so what that might look like in a radar depiction, again, is this very heavy rain, which out at the leading edge, and then the lighter rain back behind. So this is sort of a map view. And if we take a slice through there, through that line, it looks something like this, where now we have, again, it looks something like that little depiction I was showing with the wind shear a few minutes ago too. The air is coming in this way, new cells are developing over here, right? Here's the mature, the heavily raining storms here, very deep extent in the atmosphere. And then so the air is coming in, going up, and then out the back in this front to rear fashion. But then what also happens is you start to bring air in at lower levels down from the back of the system as well. And so this is kind of the typical vertical structure of one of these squall lines, where you have this fairly narrow, heavily raining line, and then with that lighter stratiform rain back behind it. And this is, if you were looking at it from the side, this is what it would look like. And then if you remember those satellite views, if you're looking down at the top, this is where that really cold, those reds and yellows on that satellite picture are showing up, because the temperature up here is very, very cold at this top. And then this is the anvil of those storms that is spreading out, which is also, fairly cold compared to the temperature at the ground there. So that's what one of these often looks like. I'm going to go pretty quickly through some of this other stuff here, because there's a couple things at the end that I want to show, and I don't want to run over too much in time, take up too much of your time today. But what we see in these two is they often go from this symmetric view to asymmetric. So here it's kind of the same front to back. Later on, we get that stratiform region ends up to the north generally in here in the U.S. That's how it tends to look, and that's what one of those looks like on radar that we were looking at earlier. Most of that stratiform rain is up here to the north, with the new storms forming down to the south in one of these lines. All right, so you can also have these that are leading stratiform. I'm just gonna really quickly skip through some of this. We have these leading stratiform systems that, if I play an animation, might look like this. So here the line is actually behind, with the stratiform region out ahead, mainly because the wind profile is going up in the atmosphere is a bit different. And you can also have these parallel stratiform ones that look like this, where that stratiform rain is off to the northeast. And just a quick example of one of those here from Wisconsin, where it's mainly parallel. Although what you see is then it transitions into a different, to a trailing stratiform system later. All right, so that's just MCSs in general. Now, the topic that I like to talk about, because it's specifically what I study, is the ones that produce especially heavy rainfall. So the ones I was showing you there, for the most part, are moving pretty quick. And so this is where you get a broad swath of maybe briefly heavy rain, but it doesn't last all that long. And then you get this lighter rain for a time period. Not something that, this is the beneficial rain, not the stuff that is such a flash flood threat. But if the system is moving slowly, or if the cells are passing over the same area over and over and over again, which is a process we call training. So it's sort of like these storm cells are lined up along a railroad track, right? And that's where the name comes from. So it's like train cars passing over and over and over again. That some of these look that way, where you're getting, you know, one storm passes over and then another and another and another. And so, you know, if that's happening over your house or your field, then that's where these really large accumulations are developing. And so how do these come together? We looked at these in much the same way, just looking at lots and lots of radar images, but specifically for storms that produce really heavy rainfall. And so one of those types looks kind of like this, and we refer to it as a training line. And so again, imagine each of these cells is sort of along a railroad track here that's moving from left to right in this direction. If you live under here and you're getting, you know, 5 or 10 of these really heavy convective cells passing over, those rainfall amounts can add up very, very quickly. And so in this case, sort of everything here is moving pretty slowly from left to right, and you're getting new storms to form back to the usually to the west, but you know, to the left in this figure, and just piling up the rain in this area. Sort of just a very prominent example of one of these systems is back from August of 2007 in Minnesota and Wisconsin, and you can see this happen in the radar loop here. So we'll play through this. You can just see this line of storms lines up again, is almost as if it's along, you know, so there's a track here that all these storms are following, and just producing very, very heavy rainfall, particularly in southeastern Minnesota and southwestern Wisconsin. This led to devastating flash flooding in this region. Almost exact, you know, we're nearing the 10-year anniversary of this event. It was the state record in Minnesota for one-day rainfall, over 15 inches in southeastern Minnesota. And those of you that have been to this area, you know this is very complex terrain in the you know, as the St. Croix and the Mississippi rivers kind of come together in there, really, you know, very prone to flooding with this kind of rain amounts. So that's one example of this training line type system. Another type then, that it has similarities to those, is what we refer to as backbuilding or quasi-stationary. So backbuilding just refers to the system as a whole, in this case, is maybe moving from left to right, but new cells keep forming back to the west. So it's building towards the back side, and that means that the system as a whole is hardly moving. And so that system we looked at over in Missouri at the very beginning of the talk was a great example of that behavior, where you could see it, just kind of the new storms kept building back to the west. Here's another example that also happens to be from Missouri, where we saw that. This is the case back from 2000, where you just see new cells forming back to the west. You can see everything as a whole is sort of moving from west to east here, but not the heaviest rain. The heaviest rain is just sitting in one spot here just to the southwest of St. Louis. And so this event also produced a really, really big flash flood just to the southwest of the St. Louis area back in 2000, particularly the town of Union, Missouri, in that time frame. Okay, and so, right, so what's happening here is, in a sense, it's kind of a flip of that picture we were showing earlier, where new cells now, instead of forming off to the east, are instead forming back to the west, and so the system as a whole is not moving very much. The old cells are moving from left to right, but the new ones are forming to the left, and so the system produces this really heavy rain. All right, so just a couple of last tidbits here towards the end that I want to point your attention to, because it's interesting and relevant, and it's the sort of stuff that we're working on very actively in a research setting. So as you might guess, just from your own experience or from kind of looking at the complexity of some of these things we've been looking at, forecasting these things is really hard. It's hard to precipitation is one of the hardest things to forecast anyway, for lots of different reasons. I mean, it occurs at such small scales, and the processes in the clouds are really complicated, and this is even more so in the summertime. You've all probably experienced the thing where the situation in the summer where the storm pops up and it rains on your neighbor's lawn, but not yours, just across the street. Those are the kinds of scales that we're working with here, and some of those things are almost completely unpredictable. And when these systems are interacting with each other, it can become even more complicated. And so this graph on the right illustrates how this comes out in the data from the forecast. So what this shows is basically how good the forecasts are of 1 inch of rain on day one. So basically, if you made a forecast earlier this morning for the storms that would form overnight tonight. So these are forecasts from models in the green, blue, and pink, and then from the human forecasters at the Weather Prediction Center in red. And a perfect score here is 1, so higher scores are better. And what you see is the scores are relatively high in all the seasons except the summer, and the scores in the summer are really low. And so it basically just shows that even as we continue to get better at doing these forecasts, just the storms are harder to predict in the summer because of these small scale interactions that we've been talking about. And so we're very actively working on this, but it's a hard problem to do. The other thing you might notice here is that in all these months, the red bars are higher than the pink and blue and green bars, which tells us that human forecasters still provide value. They're still making the model forecast better because they understand some of the quirks of each individual model, or what things they tend to do well and what things they tend not to do well. For example, models tend to be pretty accurate in saying that there's going to be an MCS tonight, say. If we looked at the model forecast from today for tonight, they're going to show us that there are going to be MCSs in sort of a general region, but they're not very good at putting them in the right spot. And so that's what the human forecasters can do, is kind of correct for some of those errors based on their experience and their expertise. And so a field project, one of the things we tried to do to make this better is go out and collect data in the field. One of these we did is called Pecan, or Plains Elevated Convection at Night, which was 2 summers ago in 2015. We were based in Hays, Kansas, and then had groups kind of all throughout the plains. And what folks are doing is going out and launching weather balloons at night to measure the atmosphere, flying aircraft through near the storms to measure the environments there. We have really sophisticated radars out in the plains. As you can see, these are all the awesome, enthusiastic graduate students, and then what us professors get to go do is go sit in a conference room and look at our computers all night. So not quite as exciting, but also important to the process. And in any case, though, I promised I would come back to the Jeopardy thing just because it was sort of funny. So we were involved in these projects where we were launching these weather balloons, which have an instrument package that's referred to as a radiosonde. And then right around the time that we were doing this project, it was when I went back for this decades tournament, and this clue came up for me on the show. Unfortunately, I got it right. So it says that asks about what you send a radiosonde up into the sky with, and we know it's one of these balloons that looks like this. So fortunately, I didn't have to embarrass myself too much by missing this one. But we launched a whole lot of these weather balloons here to try and get this data, and we're really kind of in the midst of analyzing all of it now. This is just a map showing kind of some of the places we were. And what we're seeing is some really cool stuff about how quickly these storms, the sort of air that's flowing into these storms can change. And I'll just give you this one tidbit here before we finish. So this, along the x-axis here, is time. So this is going from 7 p.m. local time in Iowa, Central Time, to 6-7 hours later into the middle of the night. The red contours here are the instability, the CAPE. It's a measure of the instability in the atmosphere. And so what we're seeing, and so, normally the National Weather Service launches balloons twice a day. 0Z, so we would have launched a balloon here, and then 12Z, which would be the next morning, which would be off the map here, or off this plot. We were out there in the field launching balloons every 20 to 30 minutes. And so what you see in this time period is just this rapid change in the instability. So at 0Z, when the sort of normal balloon launches would be, it's actually not very favorable for storms to form. But 4 hours later now, the CAPE, which is, again, a measure of instability, goes from, maybe 500 to 1,000, which is not that exciting, to like over 4,000, which is a really huge value. And so shortly after this, there were some severe storms that came through this spot. So this is the kind of data we're analyzing to understand what kind of data we need to make these predictions better, whether we can use this kind of information to make the model forecast better and the human forecast better. Okay, so I'll just wrap up here by showing, if you're interested in monitoring these, looking at them on a nightly basis, seeing where they go, whether one's coming your way. For forecast information, of course, you're probably familiar with going to your local National Weather Service office, their website. You just go to weather.gov, you click on your area, it'll give you kind of the general forecast for that area. But based on some of the stuff we've been looking at here today, you might also be interested in looking at sort of these national perspective views, say from the Storm Prediction Center. So they predict severe weather. And then the Weather Prediction Center, which is tasked with predicting rainfall. And so they both have these kind of broad outlooks that will show you at least the general region where, say, tonight, MCSs might be expected, which in the case for tonight will be particularly over, like the Ohio Valley type region. Those of you that might be in the Wisconsin, Illinois region, you've been living with these for the last few days as well, with some really heavy rain in there. So these kind of give you a sense of where they might be expected to occur on a given night. While they're happening, there's lots of places you can get radar data. Just a couple here. The Weather Service website has a nice kind of big picture radar views, or the College of DuPage website is really great for this as well. There's lots of apps you can get for your computer or your phone. RadarScope is one that we use a lot because it's just kind of a beautiful presentation of the data, although you do have to pay for it, unfortunately. Satellite data, also the College of DuPage, or CIRA here at CSU has this pretty amazing new platform for looking at that GOES 16, the new satellite data, but it's just kind of still working the bugs out. So, on a given day that this may or may not work perfectly, but when it's working well, you can see some amazing pictures and animations. And then if you want to look at, how much rain fell the night before from the MCS that came through your area, water.weather.gov is one place you can check out there. So thanks so much for your attention, and I'd be happy to answer any questions, or feel free to drop me an email after the later on or tomorrow or whatever at my email address listed there. So thanks so much, and I guess Noah, if you've got questions.
Yeah, Russ, thank you so much. That was really great. I learned a lot myself. If you want to keep that last slide up, that's fine. However, I'll warn everyone, don't worry about writing down those long URLs. We'll provide links on the WeatherTalk webinar page next to Russ's talk here for on the website. Russ, as people are starting to type in their questions, I guess one question that we tend to ask a lot of our presenters is what got you interested in weather in the first place? Was there maybe an event when you were a kid that sparked your drive to this career?
Yeah, it's interesting. There almost always is an event as a kid that got, when you ask most meteorologists, there's something like that tended to get them into it. And yeah, the one for me was in July 1986. And if anybody is from the Twin Cities, Minneapolis-St. Paul area, you might remember it too, as that's where I grew up. and KARE 11 News had their traffic helicopter up there filming the traffic, and then all of a sudden this tornado develops right very close to the helicopter, and they're showing it live on the evening newscast. It's just amazing video to check out, and you can look it up on YouTube if you're interested in it. So that I remember being a kid and watching that and just being sort of amazed, and, at what they were showing, from this video, and also just, I mean, a little bit scared at that age. It wasn't really close to my house or anything, but it's hard to know that when you're little and it looks so real on the screen. So that's the event that really kind of got me interested in it. And also it was the time when the Weather Channel was first starting to come around. So I watched a lot of the early days of the Weather Channel back in the late 80s, early 90s that piqued my interest before I went to college and studied it and grad school and so forth.
I think a lot of us have some fond memories of the Weather Channel a few years back when it was more of the Weather Channel. But anyway, as I'm going to get to some questions here, I did want to quickly mention that I was watching you on Jeopardy when that radio sonde question came up, and I can't remember if you were competing against Ken Jennings at that time, but whoever it was must have thought, oh man, this is rigged here. So that was...
No, I probably if I was playing against Ken, then he would have beat me in on the buzzer.
Right, yeah. So let's go to our first question here. Pierre in Vermont is asking about wind shear, and specifically they say, I wonder what role does vertical wind shear play in strengthening convection and the building of thunderstorms, and is that similar to how horizontal shear contributes to the spin and vorticity and the creation of rising air motion?
Yeah, that's a really good question. So yeah, so let me try and bring that graphic back up here. Yeah, so both of them are really important to storm dynamics. And so the so in this example I showed here, it's just sort of the wind increasing in speed as you go up with height. And so this is all a very two-dimensional simplified picture here. And so in this case, you see the cold air spreading out. And so what's happening is you have you've got your pinwheel there that is causing the storm to rise. And really most of what the wind shear is doing in this scenario is just allowing new storms to form at the edge of where this rush of cold air is spreading out. Now, if we take this into a full three-dimensional picture, what we also end up with is when you have vertical wind shear like this and horizontal wind shear, as the question came in, is what can also happen is as the storms develop, they will tilt the sort of pinwheel here into the vertical, and that's where the rotation comes from for supercell thunderstorms that are rotating and then eventually produce tornadoes. And so then a lot of that's going on in the horizontal as well. And then of course even in these mesoscale convective systems, we end up with strong horizontal shears as well, with that lead to things like the say here, the transition from this symmetric structure to this asymmetric structure has a lot to do with the horizontal changes in the shear there as well. So I'm not sure that totally answers the question, but certainly both of those aspects are really they're critical, and they're difficult to sort of predict and observe for sure in these. Like this background vertical wind shear here, that's not too hard to measure with a radiosonde or something like it, but it's much harder to measure what's going on within the storms. Radars can tell us a lot about that. That's what, when you see the Doppler radar picture of the which is mainly showing you these horizontal shears, which often are associated with rotation. But it's it's not so safe or easy to be launching weather balloons, say, right in the middle of storms and that kind of thing.
Yeah, gotcha. No, thank you. Okay, Mark asks, I frequently see narrow lines of thunderstorms appear to weaken and spread backwards into a larger stratiform area. Is this simply a function of the maturity of the thunderstorms on a narrow line?
That's a really good question. Yeah, so it has a lot to I mean, I think that observation is exactly right. That's when it tends to happen is as the system is often as the system is decaying, then that's exactly what you'll see is the sort of backward progression of these heavier rain and maybe becoming a little bit less organized as it goes. And the kind of from some of the theory that we look at, a lot of that actually has to do with a sort of a fine balancing act between these two little circle arrows that we see on this graphic. So as the storms develop and intensify, the more rain is falling, and so more cold air is being produced here, which sort of increases the magnitude of this pinwheel. Say it's deeper or spinning faster, which will then tend to cause the system to tilt back over towards the back, just like you mentioned in the question. But if it moves into a region of higher vertical wind shear or something like that, it might tilt it back in the other direction. And so it's often that is what's happening, is just this cold pool, this outflow is getting stronger and stronger, and sort of the white arrow here becomes stronger than the purple arrow, which means that everything is going to be kind of tilting back and moving away from this leading edge and moving rearward. So yeah, I think that's a really good observation. It tends to correspond with the system weakening, but not always. It can kind of reorganize itself after that in some cases, but it does tend to correspond with the system weakening, at least in its overall extent.
All right. I've got two separate questions that both refer to Tennessee, so I'll kind of maybe clump them together. But Alan is asking, in Tennessee, we tend to have summer afternoon / early evening pop-up showers. How are these similar or different from the MCSs that occur in the Midwest and the Plains? And then the follow-up was someone else in Tennessee wondering about a specific event, April 21st of 2017. They had a big flood event, and was that an MCS?
Now you're testing my memory.
Yeah, that's fine.
I'm usually pretty good with these past cases. I'll not answer your question about that specific event, but I'll turn it to a different event in Tennessee, which you probably remember was the huge floods back in 2011 in early May. Especially Nashville had the huge flood then. And that was, it was two of these, well, maybe even more than two, but it was definitely 2 days in a row of these MCSs that just were not moving very much over, kind of centered over the Nashville area, but really a lot of Tennessee and Kentucky and that region. I'll have to look back at the April one because it's not coming to the top of my head there. But back to the sort of the question about the pop-up thunderstorms, I think this you can really see that in this loop too. And so where you see in the all these yellows, it makes it up to Tennessee somewhat, but it's very, very prominent right along the Gulf Coast, where you see that yellows and reds just pop up for a couple hours and then dissipate. That's what's going on there, is those afternoon pop-up storms developing and then weakening, in the evening and after dark. So those can develop into MCSs, but they often don't. So those pop-up storms. So like in the late summer, this time of year into August, there tends to be really weak vertical wind shear over the southeast. And so that's what tends to happen with these pop-up storms is with no vertical wind shear, the storms pop up. There's plenty of instability, lots of moisture, and it's warm and all that. So the storms pop up, but then they just sort of collapse more or less in the same place. And so it might produce some fairly heavy rain for a few minutes, 20, 30 minutes, something like that, but then they tend to dissipate, again, because there's not so much shear. Now, in the shoulder seasons, especially in the southeast, is when we tend to see that. So like in the spring, April, May time period, March, April, May, and then again in the fall, then that's when the MCS, and even through the winter in the southeast, that tends to be when the MCSs are more frequent in that region, again, mainly because the shear gets stronger, and that, again, because the jet stream is then drifting farther south, right? So in the sun, kind of a good way to separate the separation between the really hot air in the summertime and the cooler air is where the jet stream is, and in the summertime it's often way up here, in the northern plains or even up in Canada, and so the upper level winds are just really weak over the southern U.S. But as you get, either in the spring or the fall, that jet stream can be right overhead or just, through the central U.S. and then the shear is stronger, and that leads to the strong MCSs there, like that May 2011 event in Tennessee and Kentucky and other ones like it. It's really bugging me that I'm not recalling this.
No, don't worry about that. But for Eli with that question, maybe if you look it up, you can email him after the fact. So we'll look into that. Gail asks and she's from Texas. She's wondering if there's any relationship between MCSs and derechos.
Yeah, good. Yeah, that's a good question. So that's another one of those names that we come up with that kind of fits somewhere in this circle. So yeah, derechos are so for those not familiar, derechos is a term for really broad swaths of damaging winds that cover a large area. It got to be a really popular term back in 2012 when the one kind of went through Indiana, Ohio, and then through the DC area where this did tons of damage, and power was out for days and so forth. But these occur, of course, in many other places in the country as well. And so derechos tend to be associated with these bow echoing, these bow echo type structures. So it's a line of storms that takes on this bowing shape. And then at the kind of right where it's bowing there tends to be where the strongest winds are, right in that, I guess where the arrow would be in the bow. And so yeah, that's another type of MCS that tends to produce these. I wonder if I loop through this one again, if we see that kind of bowing in the Nebraska area here, because that's where those really strong winds were in that case a little bit. So let's see if maybe I go ahead so this is that case from a couple of weeks ago, and you start to get a little bit of that bowing structure there in Nebraska. But in some cases, it can be very, very sharp, where it's, very sharp, apex of that, and that's where the winds can get really, really strong through there. So yeah, that's a good question. The definition of the derecho actually has a bit more to do with the area covered by severe winds than how strong any of the given winds are. But it's these sorts of situations where you get a line kind of like this that then plows across multiple states, and you get these huge swaths of severe winds. So that, yeah, good question on that, and that's one of the hazards that comes with these MCSs.
Great, thanks, Russ. Dave in Texas wonders, are there any good papers to review low-level jets effects on Texas?
Yeah.
And possibly, if so, maybe we can have you email Charles with a link to such a paper.
Yeah, absolutely. Yeah, I could probably point you to more than you'd want to read. Maybe not. It's a really interesting topic.
Okay.
Yeah, if we can get in touch after, that's good, because I'm trying to think of what the sort of best one would be to pass along, and I might
Great.
think about that for a minute.
And speaking of low-level jet in Texas, this is Nolan finally chiming in.
Hi, Nolan.
Are the wind turbines high enough to reach up into the range of the low-level jet and tap into that nocturnal energy?
That's a good question. I think probably not. I'm not the expert on that, but I want to say they tend to be what, like 80 or 100 meters, maybe. And so that's certainly getting into the stronger winds, but probably not the peak of it, which is maybe 400, 500 meters above the ground. Though honestly, I'd almost be concerned that would be, if you could build one that tall. I'm not sure you'd want to, because the shears and the turbulence is so strong within those winds up there that it probably it could be too much wind for the turbines up at that really high height. So I think, at that 80, 100 meter height, is that it's again, I'm talking a little bit outside of my expertise here, but that seems like kind of an ideal spot, because you are starting to get into those the layer where the winds are getting stronger than they would be, down at 10 meters or something like that, but not where the winds get so strong that you have to worry about the engineering aspects of building something that tall.
All right, we got a couple more questions here, and then we'll wrap it up. Douglas asked, do tornadoes form in MCSs?
Yeah, that's a good question. They do. They're not. It's not the type of system that typically produces tornadoes, but in some scenarios they can, and they're really frustrating to forecast and warn for, I think, for the National Weather Service, because they tend not to last very long, and it's very hard to tell, like, in advance which part of the line might produce a tornado. So typically tornadoes come from supercell thunderstorms, and these have been studied for years, and people know pretty well how they work. I mean, it's still really hard to know which storm is going to produce a tornado or not, but really well if it's going to produce a tornado, where that tornado is going to be, and stuff like that. With these MCSs, often what happens is if there's going to be a tornado, it'll spin up in some little part of the convective line for 5 minutes, and then it'll be gone. And the radar scans are maybe only every 5 minutes, or every 2 minutes when they go into that mode. And so what happens is, the radar sees this spin up, and then by the time the Weather Service can issue a warning for the tornado, then it might be gone. And so it's a very hard warning challenge. It's pretty unusual to have really strong tornadoes in an MCS, but they certainly happen, and they can be, these quick spin ups can still be damaging, and they're certainly tricky to predict and understand.
Gotcha. Thank you. James in Texas wonders, what factors account for the steering and duration of these storms over several days?
Yeah, really, really good question. So from the big picture perspective, you have the upper level winds where the jet stream is, troughs and ridges, and that sort of thing. And so that's kind of setting up generally where the fronts are, and then where the lifting mechanisms are for the storms to form. So, like, as we went through this, just showing this time as an example here, but as we went through this animation, right, you kind of saw that it progressed from northwest to southeast roughly over this week, with the Nebraska and Minnesota one day, and then Iowa and Missouri the next day, and then Kansas and Nebraska, or Kansas and Oklahoma the next day, which was mainly just the large scale winds kind of pushing in that direction. And so that actually is fairly predictable, and that part of it is we can understand pretty well. Where it gets difficult is when the storms themselves start driving the motion of these larger scale patterns. And so again, in this one that we were looking at here, you know, if you remember that part of the, let's see if I can find it in the video here oh, that's right, I've got it here. So say this time, the storms building back to the west here and producing all this heavy rain was, the storm itself is really driving that, not so much the very large scale trough and ridge patterns. It's where the outflow, where that cold air is going as it spreads out from the storms. And so it produces this pool of cold air and it starts spreading out, and it can move off to the south really quickly, and that's something that's much harder to predict. So I can speak to this particular one clearly because this week when this was going on, I was out at the Weather Prediction Center. We're doing an experiment trying to, test out new tools for forecasting these, and part of what we would do is actually, try and make forecasts ourselves. And on each day of that week, the storms ended up being further to the south than what we were predicting, mainly because of that, the cold air is spreading out and basically pushing the large-scale fronts to the south when, if you just looked at it from a sort of a, big picture meteorology perspective, the fronts would be kind of moving slowly, but instead the storms would make the front move even further to the south, and you end up with a bad forecast. So that's kind of the complication there, and why some of these are so difficult is because we're pretty good at predicting the large scale patterns. We measure that pretty well, where the fronts and the troughs and the ridges are going to be. But it's when the storms start altering that things get complicated, and that can be a huge driving factor for the steering of the system, where the upper level large scale winds are steering it in one direction, but the storms themselves are trying to push it off in a different direction.
All right, thanks. We're down to our last two questions. Tommy in Virginia is asking, has stratiform rain been known to cause flooding? Could it be when the rain is yellow on the radar, that stratiform, can that cause flooding?
Yeah, it's a good question. It can. Find a good example here. Let's see. Where did I go? Well, yeah, we could take. Well, let me go to this one here. So, right, flooding is kind of a combination of the rainfall, of course, but then also what happens to the rain once it hits the ground, and what the landscape is like and how much rain has fallen previously and so forth. And so you can imagine a situation like this where a line moves through, it's producing really heavy rain, but it doesn't last very long in that initial rain, but it gets the ground wet, it starts to fill up the creeks and the streams, and then this stratiform rain region, the yellow on the radar, comes over and sits over there for another 6 hours. That initial heavy rain kind of set the stage for the lighter rain to then cause the flooding. So it's not as common, but it certainly that sort of situation can happen, and so much of that depends on what the underlying landscape is and stuff like that. I mean, honestly, say along the East Coast there in Virginia or the Carolinas, a lot of the rain that falls in, when sort of weak tropical storms come nearby, if a big hurricane makes landfall, that's a different story. But if you have sort of a weak system that comes and makes landfall, a lot of that rain is not really heavy not convective rain. It's a bit more stratiform rain. But if the storm is there for 3 days, then that moderate rain for multiple days in a row can certainly cause lots of flooding issues as well. And the same thing can happen with the stratiform rain in MCSs.
All right, thanks, Russ. So the last question, and actually I'll mention a comment too from the same location. Patty around the Minnesota-Wisconsin border mentions just thank you for explaining what she watched early yesterday morning. It was trains over them over northern Illinois for about 4 hours, and they got 7 inches of rain. And so thank you for explaining everything. She learned a lot today of what she just witnessed in the last couple of days. The question, though, comes from Travis in Minnesota, and he's wondering, why would low-level jet not occur at night?
Yeah, good question. Yeah, so I think if there's sort of not, if there's not much else going on, the low-level jet is going to be there. Where it will tend not to occur is, say, if a big cold front has come and swept through, the central U.S. and has moved down into, moved all the way down into Oklahoma, say, then just the large scale winds back behind that front are going to tend to be out of the north and just bringing kind of that cooler air mass through. And so that there might be still a low level jet, but it's only localized down to Texas, say, in that scenario, and isn't making it all the way up into Nebraska or Iowa or Minnesota, that sort of thing. So those tend to be the situations, and that's a pretty, again, this example at the beginning is a fairly good example of that, where by this the sort of the third day in this loop, this cooler air has pushed down from the north, and so most of the winds up here in the Dakotas and Minnesota are now going to be out of the north at low levels, and it won't be conducive to that low level jet, but you would still have the low level jet going to the south of that front.
Great. Thank you so much, Russ. This was a fantastic webinar. We've all learned a lot. Folks, mark your calendars and please join us for our next webinar. It's coming up on Thursday, September 7th. Jamie Rome of the National Hurricane Center in Miami is going to talk about storm surge, which is going to be very interesting and quite timely. Finally, again, to remind you when signing off today, if you can take the survey that pops up on your screen, we would appreciate it. So until September, this is Noah Newman for the rest of the CoCoRaHS headquarters team saying so long for now and wishing you all a good afternoon. Thanks so much, everyone.